Thank you, Clay. Welcome to this week's Tuesday webinar, to squeeze or not to squeeze, that is the question. So we'll be spending the next hour talking about various squeeze applications, techniques, why we want to squeeze, why we may not want to, and have a question session at the end. For those of you who may not know me, I worked for Halliburton for 34.5 years on the pumping side. Spent several years in operations. I worked in the Technology Center as a cementing global advisor. I was also a cementing technical instructor at Halliburton's training facility. I've been on location for over 500 cementing operations, including several squeeze jobs. Currently, I am the course director for Petro Skills for the two courses, Primary Cementing and Cementing Practices. And you can reach me through LinkedIn. All right. Just a little bit about the legal bit. I'll just leave this slide up a few seconds and let you take a look at it. This is a webinar. It's not a class. The presentation that I am giving on squeeze cementing is part of a bigger presentation that I give in one or both of the classes. So with that being said, we will go ahead and start the technical part of this presentation with a brief definition of squeeze cementing. Okay, I want to read through this slide and also the next slide, and then I'll talk about them together. By definition, squeeze cementing is the process of applying hydraulic pressure to force or squeeze a cement slurry into the desired perforations, fractures, channels, or voids, and force filtrate water from the slurry to create a solid mass which will harden to provide the desired seal. Squeeze cementing is as much an art as it is a science. Area experience is essential to success. Now, looking at what we talked about on the previous slide, how is this different than conventional casing cement? Well, in conventional casing cement, we are calculating volumes of cement based on data given to us from a wellbore geometry standpoint. So we know the hole size, we know the open hole based on a caliper, we know the pipe OD, so we can calculate a volumetric fill to obtain barrels, cubic feet, or sacks of cement. Squeeze cementing, trying to determine the exact volume of cement required to achieve a job, it's not as simplistic. You probably have as good a chance of guessing the next Powerball numbers as you would the exact number of barrels, cubic feet, or sacks that it will take to assure a competent squeeze job. With that being said, and later in the presentation, we'll talk about some rules of thumb that can be used to guide us in calculating volumes. But look at that last sentence. Area experience is essential. Squeeze cementing in California is different than it is in the Northeast, different than it is in South Texas, different than it is in Norway, Middle East, and South America. So having somebody who has some experience squeeze cementing in a given area is a plus. Well, the first thing, if we're going to squeeze, we're probably squeezing because we have a problem. And we need to identify what that is. In one case, it is unwanted production that we're trying to shut off. In the case of an oil reservoir producing over time, it becomes depleted, and that may allow for water coning from below, or if it's got a gas cap, gas migration from the top. So identifying the source, where it's coming from, whether it's channels or what exactly is the volume it is, that will guide us into coming up with a solution. All right, some criteria that can be useful in helping us determine whether we need to do a squeeze job. Acoustic tools, sonic, CBLs, ultrasonic tools are very good tools. They can provide very good information, albeit they may not be the tell-all as far as what we need in determining if we need to do a squeeze job or how to successfully operate and complete it. And we'll talk about that more on the next slide. The primary cement job design itself, was it modeled? The simulator, what did it tell us it was going to do? What's the slurry design? The spacers and the flusher system, the mud system, the centralizers or the hardware on the casing, everything that, from a design standpoint, that's good information. How did the job perform on location? And this begins with running the casing in the hole. Actually, probably begins before that, but running the casing in the hole. Did we lose circulation while running in the hole? Did we hit tight spots and see an increase in pressure and have to wash pipe down? Were we able to get the casing to bottom successfully with, or did we have to wash it down? The job itself, the primary job, did we lose circulation during the job? Did we have gas flow, gas intake? Did we have pressure spikes indicating maybe plugging was going on in the annulus? And the mud properties themselves, all that is critical in looking at the post-job analysis. Also, the differential pressure. We've already ascertained that we can calculate volume of cement on a casing job. Well, there's a differential pressure from, as we displace the fluid, that differential pressure should be based on the height of determined cement in the annular area. Was that close? Was it far off? Why was it far off? And just experience in a given area. If you're doing infield drilling, there should be some offset wells that can provide some data. If you're squeezing on a well, that is an area where other squeeze jobs have been performed. A lot of good information to be learned from those. All right, we're going to spend a little bit of time on this slide. What you see on the left is a picture of a full-scale test from a 60-foot test well. Service companies have capability, some of them, of doing full-scale testing, displacement studies. Some operating companies may as well. So what you're seeing here is a post-mortem of a displacement test that was cemented in the well and taken out, and then it can be cut up and evaluated in 1 or 2 foot sections. So we start off with a simulated formation. I hope you can see my mouse pointer. And this formation has permeability, capable of having leak off. And then we have our steel casing that is in the well. And if you look at this, the steel casing appears to be fairly concentric in the wellbore, which is a good thing. Out to the side, we see water-based mud, and this water-based mud appears to be having tendencies with regard to progressive gelling, not very good leak-off control. So we see leak-off going into the permeability of the simulated formation. And then we have set cement that surrounds the casing. Now, one thing you need to know about a cement slurry, it is intrinsically lazy. A cement slurry is going to seek the path of least resistance, and it's not going to work any harder than it needs to. So what we have in this case is the casing was placed concentrically in the simulated formation, and then the well, as is done in operations, the mud is circulated around, and then the cement is put in place. So the water-based mud that is close to the formation and has higher leak off, it tends to become less mobile, a higher solids to water ratio. Whereas the mud that is closer to the casing tends to be more mobile. So when the cement comes in a vertical well, exits the bottom of the casing and begins to head north, or if it's a horizontal well, heading east and west, what it's going to do is it's going to displace, being intrinsically lazy, the more mobile mud closer to the casing. and it's not going to worry about displacing this low mobility mud on the outside. So one of the things that when we go to run a CBL, cement bond log, those of you who are familiar with cement bond logs, it has a transmitter and 2 receivers 3 and 5 feet from the transmitter. And it emits an echo from the transmitter, and it hits the casing, and then it resonates down and is picked up in terms of microseconds in the receivers. When you have no cement around the casing, what you're going to hear is almost like a sonar ping sound, and the sound's going to resonate very quickly and being picked up at the receivers. And also on the amplitude curve, you're going to have very high positives, very low, very high negatives on the amplitude curve. Now, a cement casing that is encased with cement behind it like this is, instead of a ping when it hits, it's going to be more like a thud. And the transit time is going to be slower, and the amplitude, both the positive and negative side, are going to be substantially reduced. So if someone were looking at a cement bond log and looked simply at the amplitude and saw the amplitude curve very low, there might be an indication, a false indication that they have good cement throughout. And in this picture, they do have good cement around the casing. But also about the CBL, cement bond log, if we have good cement coupling all the way around, we should see some formation arrivals. In this particular case, we may not see any formation arrivals, or we may see, if we do, they're very weak. So the CBL may not be giving us the full picture of what's going on here. And we may make decisions based on amplitude, which are probably not for the best. So we've ascertained that we have a problem here. Now, what are we going to do about it? Well, we may not have to do anything. Now think about this. We perforate through the steel casing, through the cement, through the mud, into the formation, and we attempt to establish some type of injection rate. Well, we have something that is back here, and yes, it's not cement, but it's semi-solid, for lack of a better term, and we may not be able to physically displace this. So all we may do is just pressure up. And also when we do a pressure up on the casing, there is a certain amount of expansion to the casing from the pressure to the cement, and any channel back here becomes even smaller. So in a case like this, what we may want to look at doing is, if this is our production zone, also on this thing, we cannot see 10 or 15 feet on either side of it. There might be sufficient cement and sufficient isolation. I suspect not, looking at this picture, but that could be the case. But what we may want to do is perforate for production, and then if we have unwanted production coming through here, or if the hydrocarbons are going into the channel, we at least have a flow path. Having a flow path helps us be able to put cement into a confined area. So the 2 takeaways from this slide is cement bond log may not tell us always the full picture of what's going on, and we may not, if we identify a channel, we may or may not have to address it immediately. All right, do we need to squeeze narrow weight? Cost considerations. You may have to have a rig out there anyway for completion, but if not, you're going to have to get out there to squeeze with. You have to get the cementing equipment, the trucks, downhole packers, if you can squeeze with a packer, a reverse circulator to drill out, a tank to do flow back in as you drill out. So those are all upfront costs. We just talked about the equipment. Time delays for after the fact squeezes. You got to wait on cement, wait on it set, go in and drill out. In well construction plans, if you're squeezing, you may have put additional perforations into the casing, into the pipe, and nobody wants to have any additional holes, any more additional holes into the pipe than need be. Let's talk about some squeeze techniques. specifically high pressure squeeze and a low pressure squeeze. High pressure squeeze by definition, surface pressure plus displacement fluid hydrostatic plus cement slurry is equal to some bottom hole pressure that exceeds the formation fracture gradient. So you're just fracking the rock. Conversely, a low pressure squeeze is a surface pressure plus displacement fluid hydrostatic plus cement slurry hydrostatic equals to some bottom hole pressure less than formation fracture pressure. Now, one thing to note that's different here than was on a previous slide. For the cement slurry, low fluid loss cement. Low fluid loss cement is critical when designing a low pressure squeeze. Think about what we're doing here. We're taking a cementatious material, a grout, and we're trying to force it through a very confined area, whether it's perforations, whether it's corrosion holes, where it's casing split. So squeezing it over time, under pressure, the tendency is to want to physically squeeze the water out of the cement. And we don't mind that happening, we just don't want it to happen immediately. Because, and we'll talk about fluid loss versus filter cake a little bit later in the presentation. So low fluid loss cement is critical to getting a low pressure squeeze. Now, what do I mean by low fluid loss cement? I'm talking about something with an API fluid loss under 100 cc's in 30 minutes. There may be cases where you need to have it below 50 cc's, but definitely under 100 cc's in 30 minutes. And again, we'll talk more specifically about why that's important later in the presentation. Pumping techniques, hesitation squeeze and a running or walking squeeze. Starting with hesitation squeeze. In this particular case, we've got a surface pressure limit set at 2,000 psi. What we do is we begin to mix and displace cement. And at some point, the cement begins to enter the formation, the perforations, and we begin to see a increase in pressure. And ideally, we'd like to see it continually go up. But at some point, this curve may go and begin to flatten. We flatten the curve. Man, we've heard a lot of that in the last few months, haven't we? So we flatten the curve. And so we're not building any pressure. A decision is made to go ahead and start hesitations. Hesitations, we physically shut down the pump for a period of 5 to 10 minutes. And we're allowing the cement that's in the perforation tunnels to begin to lose some filtrate, build some strength, build some resistance. And we apply the pump pressure and we build up a little bit more pressure and then we shut down. And these are hesitations. And ideally what we're looking at, every time we put a pump on it, we're going to build up additional pressure. It's going to get higher pressure, and when we shut down, we're not going to lose as much. So we're working this sawtooth effect basically until we get to the maximum pressure where we're no longer able to pump into it below the maximum pressure that's set. And when we shut down, we don't lose any pressure. So we hold it for a few minutes to make sure it will hold. Then we release the pressure into the displacement tanks on the cementing unit. And we look at the volume coming back. And all we're interested in is the volume of fluid coming back into the displacement tank. Basically, it took the charge the system to the pressure. You know, that might be a barrel a little bit over. That's all we want to see. We do not want to see continuous flow back. If we do, we apply additional pressure and wait longer. So we allow it to flow back for a period of time, ascertain that no more is coming back. We apply additional pressure on it, make sure everything's okay. At some point, we release the pressure, release the packer, or sting out of the packer. If it's a drillable packer, come out of the hole, wait on cement, go back in and drill out, pressure test. Now, one thing we want to be aware of here is, or a couple of things, when we start this process of hesitations, ideally, want all the cement to be below the packer when we begin the hesitations. So this may determine where you place the packer in relation to the top perforation. I've said it before, I'm going to say it a few times during this presentation, experience be your guide. So if somebody has experienced squeeze cementing in an area, they can provide guidance on adequate distance to place the packer above the perforations. The other thing from an operational standpoint is when we do this, we do not want to exceed the thickening time, working time of the cement slurry, because at the end of the operation, we're going to have to reverse excess cement out of the tubing if not all of it is below the packer. So we want to allow enough time to do that operation. And squeeze pressure in the perforation should not be confused with thickening time, because we can obtain a successful squeeze at the perforated interval and still have enough working time to be able to release the packer and reverse out excess cement. But we never want to exceed the working time of the cement. And we'll talk more about this working time on a couple slides ahead. So that's a hesitation squeeze. Conversely, we have a running or walking squeeze. Again, we have a 2,000 PSI surface pressure limit. We begin to mix our cement, displace it. Cement begins to enter the formation. And what we have here is the cement pressure into the perforation is continuing to walk up. We don't see any attempt to break over or flatten. And as long as the pressure is increasing, one can just go ahead and keep a pump on it and just work it up, and it'll just walk itself into a successful squeeze. And as you did before, hold the pressure, release the pressure, bleed off, check the flow back, apply pressure, make sure everything's still good, and come out of the hole, wait on cement, and go in and drill out and pressure test. This is an ideal situation. If you can walk into a squeeze like this, this is the preferred thing to happen. But as far as which method works, you know, again, the experience thing, and let the well tell you what it wants to do. So if you're displacing and you're not seeing this curve, this build up, at some point the decision's going to be made, well, let's just shut down. Let's wait on it and see what it does. So at some point in here, if we don't see a continuous break, pressure increase, we want to wait and see that and start doing hesitations. So that's a running and walking squeeze. We talked about hesitations. We need to be aware. I think it makes some sense that looking at a cement slurry that we're not doing hesitations, the thickening time is going to be, and working time is going to be a good bit longer. In this particular case, I think it's about 2 hours longer than the same slurry doing hesitations on. So you just need to be aware of that a cement slurry that maybe you look at in the API cementing casing schedules. If that slurry pumps at something a certain amount of time, that may be without any hesitation. Now you can actually test this in a laboratory on an HPHT consistometer. You can test the hesitate. You can program it to where it'll stir the slurry for a period of time, then shut down, and then kick back on. Or you can manually shut the machine off and on. But if you're working in an area where there's not a lot of experience in hesitations and not a lot of experience in squeezing, I would strongly suggest, if you believe you're going to be doing hesitations, that you test it in a laboratory to give you a good feel for what the working time of your cement is. You may just want to do it anyway. That's hesitation of thickening time. All right. From a placement technique standpoint, squeeze packer, or are we not going to use a squeeze packer? Using a squeeze packer applies some benefits to us in that we're able to isolate the casing, especially the uncemented part of the casing, from any working pressure into the perforated interval. So any pressure applied into these perforations is not being applied to the annular area. And this is critical, especially when you get above the top of the cement. And normally there will be some annular pressure applied prior to the cementing operation, pump down the tubing. That annular pressure is twofold benefit, helps provide additional support to the packer in the well, and also provides some support internally to the casing. One thing, and this bottom bullet talks about it, is when you apply squeeze pressure through your perforations, depending on where your top of cement is, if there's natural fractures or some way of communicating in the formation, you can transmit pressure back and have it applied to the casing above the top of cement and run the risk of collapsing the casing from above. And that's very undesirable. We don't want that to happen. So we have a choice of packers. We have a retrievable or a drillable. And I think most recent surveys showed that it's about 50% on each one where they're run. And again, experience in a given area will be a guide for that. There's advantages and disadvantages is to both a retrievable or drillable. First, let's talk about a drillable packer. The drillable packer is designed not to come out of the hole. It's a one-set, one-time packer. And when we're finished with the squeeze cementing operation, after we wait on cement, we're going to come back in and drill out and pressure test and check for competency of the squeeze. So since it's not designed, the drillable, to come out of the hole, we can maybe be a little bit more daring with it, leave some cement on top of it, and I'm going to talk about a technique a little bit later in the presentation where a drillable packer is a must. A retrievable packer is not an option. And some of you experienced with squeeze cementing probably are ahead of the game, know what I'm talking about. But and another thing about the drillable packer is in a vertical well, we can set it with a wire line. That may be advantageous where depth is critical. We have to set it within a certain depth and get it set on a certain interval. So wireline may be beneficial in that regard. The other thing about a drillable packer is once we're finished with the cementing operation, we physically sting out of it, and there's a valve that closes, so it's almost like we have a bridge plug at that point. So we're going to go ahead and when we reverse out, any operation that is now taking place above the packer will not interfere with the squeeze cement below the packer. Now, one thing about drillable packers that may lend itself to not being as positive is, as I mentioned, it's a single set type of packer. We're not coming out of the hole with it. So in the case where when we set it and we want to establish an injection rate prior to pumping in cement, make sure we can pump injection into the perforations, that we may get into a scenario where we attempt to pump into it and we can't. Either for some reason, maybe the gas didn't fire effectively, maybe there's debris in the perforations. So now we have a situation with a drillable packer in the hole, and basically our only option is we're limited in what we can do is go back in and drill it out, come out and go in and reperforate. If we were to have a retrievable packer in the hole, and that scenario presented itself where we could not establish an injection, an option would be to release the packer, go down right above the perforations, spot some acid across the perforations and attempt to break it down doing that. The other thing is with a retrievable packer, after we squeeze, we can come up the hole. After we reverse out and clean out, we may want to do some other activities up the hole, up the casing. So retrievable or drillable packer, area specific as to which one's more beneficial or what you want to do. Both tools are used. Both tools are used successfully. As I mentioned earlier, about 50% of the time on each one. Alternative to using a squeeze tool method is not using a packer, and this is called a Bradenhead method. So an opportunity for a Bradenhead method would be if we have an extremely long perforated interval where we want to squeeze the perforations off. One thing we can do is with the Bradenhead method, we don't have a packer, we just go open-ended with the tubing, go below the perforations and circulate to surface, circulate cement across the entire perforated interval. Kind of like setting a balanced plug, for those of you familiar with doing that. So we start off with having cement across the entire perforated interval, and that's beneficial. So once we do that, we go ahead and pull the tubing up the hole above the top perforation, isolate the annular area, and begin to apply pressure down the tubing and squeeze the cement into the perforations. So now one of the disadvantages of the Bradenhead method, we're limited in pressure because the entire casing annular area is exposed to whatever pressure we're applying on the squeeze. So we have to be aware of that and address that and understand that. Now, one thing that can be done with the Bradenhead method that is somewhat of an optional is after the job, we obtain the squeeze pressure. And remember, the first place we're going to see squeeze pressure is at the perforations. So we want we're going to reach a squeeze pressure before we reach the hydration time of our cement. So we've obtained some squeeze pressure that we feel comfortable with, and an option that can be done is to go back into cement that's still in the casing and circulate it out to the surface. That saves the cost of drilling out, the time and expense with drilling out. So we've got that. Now, I throw that out as an option because there may be some discomfort in doing that with the thought that if I go back down and circulate across my perforations, I may disturb the cement that's in the perforated interval. And honestly, some people like the comfort of being able to come out of the hole, leaving the cement, and come back in and drill out good hard cement. But that is an option with the Bradenhead method. Yeah, the Bradenhead method is a squeeze technique that is used without a packer. There's another form of a Bradenhead method, and that is using coiled tubing. Those of you who are not familiar with coiled tubing, talk about a special alloy metallurgy, small diameter tubing that is wrapped around a real mobile unit, and it may be anywhere from, depending on the unit itself, 10 to 15,000 feet that is on the unit. And the way we use a Bradenhead method with the coiled tubing is, in this illustration, we have casing, and we have perforations in the casing that we're attempting to squeeze. We also have tubing in the well, and we have a packer sealing off the annular area between the tubing and the casing. So the benefits of a coiled tubing use with the Bradenhead method is with the fact that we have a mobile injection point. So there's an injector up at the surface that is physically injecting the coil into the tubing and down into the casing. So We get put the coil below the bottom perforations, and we begin to pump cement into it. And as we pump cement, we are going to be layering it in there. We're also, since we have a mobile injection point, is to begin to reel up the coil, and we're going to be layering the cement across the perforations. And once we get above get all the cement out of the coil, we're going to apply some back pressure, because at this point, we don't want to be circulating the cement back up. We want to be forcing it through the perforated interval. So the advantage of looking at a coiled tubing unit, in addition to having a mobile injection point that allows exact placement, we have a very small diameter. In many cases, the idea of the coil may be inch and a quarter, inch and a half. So it's not very big. So less likelihood of contamination going down. So we can potentially get by with smaller volumes of cement using this, because we have exact placement and contamination is less. Some operational concerns with regard to the coil. Say an example, if you're working 3,000 feet from surface, vertical, and you have 10 to 15,000 feet of coil on the unit, you cannot simply isolate 3,000 feet and pump through it. You have to pump through the entire reel length on the unit. And since the ID is very small, you cannot pump at a very high rate. So you're limited with rate. So additional concern needs to be looked at with regard to the slurry design itself. To pump a cement slurry in that type of environment and make it conducive to flow and move, there may be materials added to it to make it more rheologically fit for that type of environment. I'm talking about adding materials like dispersing materials, which is fine if that's what's needed to be able to pump it in there. But the thing need to be aware of with dispersing materials is, as they thin the slurry, we still want the slurry to be stable. Slurry stability is a key. Slurry stability is a key at any point, but especially in an application like this, because we don't want to be pumping at a very low rate and have separation of solids and water, create problems. I've heard of a case where, with a coiled tubing cement job, that the cement slurry being pumped through the coil pretty early in the job, may not even have gotten all the way through the coil to the bottom of the well, and the maximum surface pressure was reached. Well, so the job had to be aborted. And as part of the post-mortem, looking at it, it was discovered that the slurry had settled out and bridged inside the coil. So that it can happen. I don't mean to frighten anybody away from using coiled tubing, because it's a good application, good from a standpoint of having a mobile injection point and an exact placement of a cement slurry. But we just need to do proper lab testing. And the other thing with coil that might help that is, since we're talking normally about very small volumes relatively, that the entire slurry could be batch mixed at the surface, either in the recirculating mixing system of the cementing unit or a separate batch system. So that would help. That would help eliminate any error from continuous mixing, that we can batch mix it. We know the exact amount of water to mix X number of sacks and get it to the density. So that's a coiled tubing method as a form of Bradenhead. I mentioned earlier that there are some rules of thumb that could be used to guide us with regard to coming up with volumes of cement on squeeze operations. Number one, if an injection rate of 2 barrels per minute can be achieved, a minimum volume of 100 sacks should be used. Otherwise, use a minimum of 50 sacks. Second bullet, for every foot of perforations, use 2 sacks of cement. Number 3, area experience supersedes the first 2 bullets. The fourth thing, and this is a calculation that I would strongly suggest you make prior to every squeeze job. make the calculation to determine if a cement column can be safely reversed out. Example. We've established an injection rate with a linear fluid. Consistency of water, it might be water, it might be treated water. We're able to establish an injection rate. We mix our cement slurry, we place it down into the well, cement slurry gets to the perforated interval, and either very little goes in or none goes in when it hits the perforations, and we pressure up. So now we have a column in the tubing of a cement slurry that we need to do something with. Well, what we're going to do with it is we're going to have to reverse it out of the well. Well, when we reverse it out of the well, we're going to have a differential pressure of the lighter fluid in the annular area once we release the packer or sting out of the retainer or drillable packer. So that differential pressure to reverse out, we need to know what it is in the worst case scenario, and we do not want it to exceed the internal yield of the casing. So that is a calculation that needs to be made, that if we need to reverse out with all the cement in the tubing, what would that pressure be? Let's talk about fluid loss control versus filter cake development. Okay, this is a slide. This is a perfect illustration of bigger is not better. It's what we have here. Going with a high fluid loss cement, 1,000 cc's. So now I think they're probably being generous with this. I think a deep cement slurry may even have a higher fluid loss than this. But then as we add fluid loss control to our cement slurry, we see reductions in fluid loss. And what these are here, the cement as we squeeze will build up nodes on the perforations. This is a cement node. And by node, I'm saying N-O-D-E, node. And these nodes actually exist. I've seen a downhole video camera run into a well after a squeeze operation, and seen on the perforations tunnels, I've actually seen these nodes. In fact, the downhole video I saw had the nodes were more symmetrical than they are here. These are jagged. So let's look at this neat cement slurry that has no fluid loss control. So again, we're squeezing cement into a very confined area. So what is happening is the water is squeezed out of the cement slurry in a very high rate in a very short period of time. And so it's building a mass behind it that is not very competent, and I'll speak more on that later. So what it's doing is it's providing some restriction in the wellbore if you build this. So what could happen if you have a situation like this, you may get a false indication of a squeeze because you're restriction pressure, and you may not be able to squeeze any cement down below this interval. And what may happen if you waited on cement and you came back in the drill out, I suspect what happened is you may not even have to drill this out. You may be able to just wash right through it, and if you did a pressure test, I think you'd find that there was not a competent seal in the perforation tunnel. So this is why we want to get down to a lower fluid loss control and better fluid loss control, down below 100 cc's. Even though we have a smaller node built up on the perforation tunnel, it is a lot more competent, a lot sturdier, and will withstand a pressure test. And the next slide will illustrate this even further. All right, I want to look at this slide. I always like to look at the first and third columns first, then we'll go to the middle column. So the far left column is API fluid loss, and we go from higher to lower. And then if you look at the third column, you see how long it takes to physically build a 2-inch filter cake. You see a high fluid loss cement does not take very long at all. Whereas you have something down at 50 cc's in 30 minutes, it's 100 minutes to build it. And if you look in the middle column then, in reference to the various fluid loss, you'll see that you have, that actually tells a story, going back to the previous slide. you have a lot more competent, lower permeability filter cake with a low fluid loss cement. And that's why for low pressure squeezes, we want to have good fluid loss control in our cement slurry. You remember earlier I mentioned that I would talk about a method technique where a drillable packer is a must. A retrievable packer is not an option. This is it, circulating squeeze. You notice the first bullet point says suicide squeeze. That's not a nomenclature I'm comfortable with, but the reason it's on here is there's folks out in the industry, in the patch, who are familiar with this term. So you might hear it and understand that is talking about a circulating squeeze. The circulating squeeze allows us to place cement into long intervals of uncemented annular area that we've identified. So we've identified in a well that we need to place cement to isolate a zone. So what we do is we go below the zone of interest and we perforate, shoot perforation holes. Then we go above the zone of interest and we shoot some additional perforation holes. We set a drillable tool above the bottom perforations and we establish an injection rate. We're not pumping cement yet. We're establishing an injection rate just to make sure we can place cement. And it exits the casing through the bottom perforations, comes up the annular area, back into the perforations, and then to the surface. So in actuality, this is not a squeeze in the sense that we've been talking about it, pumping cement into a confined area. We're actually establishing circulation, but it's a good technique to place cement. Once we establish circulation, we're going to go ahead and mix our cement, pump it down into the annular area, up, back into the casing, and place it, and at some point sting out of the retainer and come out of the hole. Now, what may occur here, since we have a retainer, we're pumping cement on top of it, some cement may fall and sit on top of the drillable tool, which is okay. We're not coming out of the hole with it anyway. So once we finish the operation, we can physically sting out of the drillable tool, come up some point above the top perforations, reverse out, come out of the hole, wait on cement, go back in, drill out, and pressure test. And then, I don't know that we can run a cement bond log, but if we've ascertained that we've circulated cement back in here, then we may not need to do that. So that's a circulating squeeze to be used with a drillable tool. The abandonment squeeze. In the case of, in the life of every well, it gets at some point, it's no longer economically productive. And the decision is made to physically abandon it. Well, to do that, there are certain guidelines that must be followed. There are regulatory agencies within each oil and gas producing state and also in various countries that provide these guidelines that we have to adhere to successfully abandon a well. And some of these guidelines may be the same among the states. They may vary little, or they may be a good bit different. But I think one thing that is very close to the same for all the wells is some cement material needs to be pumped into the old production perforations to isolate them, successfully squeeze. So in this case, we have a drillable tool that is set above the top perforations. The tubing has been stung into it. Cement slurry is pumped down below, squeezed into the perforation tunnels. We come off the retainer. The valve closes and may just for added insurance, dump some additional cement on top of the drillable tool and then come out of the hole. And that's how you abandon squeeze perforations, or you abandon perforations in a production interval. And there's, depending on the regulatory agency, there's other guidelines what to do further up the hole for other formations, and setting plugs at the bottom of the surface casing may be something that is added on there too. So just reach out to your local regulatory agency, work with them, find out what the exact guidelines are for successfully abandoning a well. All right, channels. How do we address channels? So in this particular case, we've got two different methods. On the left-hand side, we've identified through production perforations, these are production perforations initially. We have unwanted production, and this unwanted production is water, and we've identified from logs, open hole logs, that we have a water zone below the production. So we've made ascertained that water production is coming from below. So we have a channel, which is good from the standpoint we have a flow path. It's more easily to squeeze a cement slurry into a flow path. So we can squeeze cement into this channel and isolate this water zone from the producing interval. Now, you know this from the drawing, and drawings are wonderful, they're simplistic, and give you a good view that we show a channel on one side of the pipe. In reality, this is probably what's going to happen. In the cutoff I showed very early on about the mud ring, it was circumferential around the entire pipe. Likelihood, if you have a channel, it's not going to be like that. It's going to be on one side of the casing. So that's one option on how we could attack that. The second option is to do a circulation squeeze. So what we do is we go down into the unwanted production interval, the water, we perforate, and we establish an injection rate back into the producing holes above, and we circulate cement through the channel from below back into the casing. Now, a couple things to be aware of here is that if we're going to perforate with the intent of filling this channel from below, then we have to have a pretty good level of confidence that wherever we perforate is going to intersect the channel. So you might want to think about that, and then if you decide to go this route, how are you going to orient your perforations around the casing to make sure that you give yourself the best chance of success. The other thing with regard to doing this second method is now we have additional holes in casing that we have to deal with. So we have to be assured after this operation is complete that we have a competent seal through these perforations here as we begin to work production up here. So that's a circulation method on how to work through channels. All right, this is the slide we've been looking for. This is the last slide. Squeezing into highly fractured bugular zones that have a good bit of lost circulation. Attacking these particular environments, hesitation squeezes may not even work because you shut down, allowing your cement to do something, and it may just physically just pull it in, and it just won't build anything. It won't build anything before all the cement is pulled into the perforated interval. So we have to get a little creative doing this. And by creativity, we may look at a multiple stage system where we have a tail and a lead slurry or system. So the lead system is going to can be composed of some type of fluid that has lost circulation material in it, high fluid loss cement, thixotropic cement, foam cement, quick setting cement, reactive pre-flushes. And the reactive pre-flushes can be something that reacts with the formation brine, the drilling fluid that may be in the wellbore, or even reacts with the tail cement as it comes in. And all we're wanting to do with this lead or first stage is to get something out that will build a barrier that we can build against with the tail system that is composed of low fluid loss cement is what we want. Is we want that competent seal at the perforation tunnel. That's all we want from the lead slurry. And so that's how you'd want to attack the fracture or vugular zones. So with that, that concludes the presentation, and I will direct it over to Clay for any questions that have come across.
All right. Thanks very much, Bob. We do have some questions that came in throughout the presentation, so I will start going through those. And as I'm doing that, if there are additional questions, feel free to go ahead and put those into the chat. All right, so the first question here says, in the various squeeze types, what dictates the pressure limit shown on the pressure versus time graphs?
Good question. The pressure limits are set by the number one, the formation. If you're doing a low pressure squeeze, which is desirable, you need to have you want to stay below that. So do some calculations that take into account the hydrostatic of the fluids in the wellbore plus wellhead pressure. And so that's one aspect. The other aspect of the surface pressure is going to be tied to the surface equipment, the valves you're pumping through, the wellhead, and then also the internal yield of the work string that you're pumping through. So all those should be taken into consideration when setting the maximum surface pressure.
Okay, thank you. The next question, I'll paraphrase a little bit here, is how do we do the right injectivity before doing a squeeze job?
Well, first we want to do an injectivity without the cement. We don't want the cement slurry to be the first fluid that we try to pump into the formation. So the right injectivity, we want to make sure the fluid that we're using is a clean fluid. It's not something that is pulled out of the bottom of a tank, because we don't want to be pumping material in the water that may plug off the perforation. So it's got to be a clean, linear fluid that has little to no viscosity. And you can use water if the water is treated with maybe some KCl or some type of salt. That won't cause any problems in the interval that you're trying to squeeze.
All right, and then a few different people asked versions of this question, but the gist of it is what is the approximate success rate, or in your experience, what's the chance of success for a good squeeze?
I'd say it's pretty good. I really do, and it's just getting the right method in that experience. And I hate to default to that, but keep going there. But area experience is critical, and knowing the type of cement slurry, knowing where to set the packers, knowing above the perforations how much volume you're going to use to squeeze and to hesitate. But if you're squeezing perforations, the success ratio is really pretty good. If it's properly designed and the experience level is there, it should be fairly routine.
All right, and so then kind of a follow-on question to that are, what are some common reasons why a squeeze job would not be successful?
Maybe not the right type of cement slurry. We can't, and I think I mentioned this, we couldn't pump into the formation, and we just pressured up. extreme losses, like I showed on that last slide, with vugular or fractured intervals. Maybe we got an injection rate, it was very high, but we decided the systems that we wanted to use, maybe we should have used multiple systems where we had a tail and a lead stage and we didn't. Those can all be factors in not achieving a good cement squeeze. And I'm hesitant, I'm trying to think of more. If I think of more, I'll come back to that, but those are the primary ones.
Okay, next question is, why is there a difference in thickening time for hesitation squeeze and walking squeeze?
Okay, when you're hesitating in cement, when you physically shut down, then you're allowing the cement to begin to build internal gel strength. It's going to begin to start hydrating. It's static, and it's going to become more difficult to move each time you put a pump on it. Continuously moving a cement slurry allows it to stay fluid longer. And that, like I said, that can be easily checked. If you want to go into the lab, take a cement slurry, put it in a machine, run a thickening time, then take the same cement slurry and do hesitations, and you will see the difference. You will see the difference in the thickening work time.
Okay, let's see. This next question was regarding channeling and connecting the hydrocarbon zone to the water zone, and it came in before you covered that slide, so I think you ended up answering it. But whoever wrote in that question, if you still have outstanding questions, go ahead and put those in. So the next question, is there a rule of thumb for planning a certain API FL in a slurry based on injection rate?
No, not based on injection rate. You still want to have a low fluid loss squeeze, and I talked about being under 100 cc's. Now, to that point, if the injection rate is very high and you're looking at an environment like we saw on that last slide where it's highly fractured, vugular type formation, then if you remember, one of the options on the lead slurry was a high fluid loss system, basically allowing it to get out behind the casing, leak off, and build a bridge. So if you have a very high injection rate, say above greater than 2 barrels per minute, and even greater than that, then you may want to consider running a multiple stage system where the lead slurry is a higher fluid loss.
Okay. Next question is, how can we avoid slurry contamination in high pressure job with retainer?
You want to put a spacer of some type to be between the drilling fluid and the cement. So having some type of spacer system. It doesn't have to be a lot of volume because you're pumping through a small ID to allow separation of fluids. Should allow that minimize the likelihood of contamination.
Okay, and then a few different questions came in regarding this subject. Is it necessary to pump high fluid loss slurry in high injectivity scenarios, or can the job be done with a low fluid slurry?
Okay, so we talked about briefly just a little bit ago, but that's still a good question from the standpoint of if you have a high injectivity rate or type of environment, the low fluid loss system by itself may not be sufficient without being able to be placed into the perforations and provide a seal there. It may just go out into the well and you may not achieve a squeeze. So in those type of environments, yes, you need to have a high fluid loss system as a lead, or there are several things: low circulation material, thixotropic cement, foam cement, reactive pre-flushes are all options as a lead system when pumping in those type of environments where you have extremely high injection rates.
Okay. The next question is, what is the relation of squeeze above and below the fracture gradient of the exposed formation?
You want to be below the fracture gradient of the formation. So I would suggest that, so whatever the weaker one is, you want to be below that. So check with the reservoir department or the geologist, and they should be able to give you an idea on what those gradients are, and I would calculate from there. If you're doing a low pressure squeeze, you don't want to exceed those gradients.
Okay. Next question is it advisable to perform hesitation squeeze in sandstones?
Yeah, it's whether it's a carbonate, a dolomite, sandstone, the formation is, as I mentioned, is going to tell you what system to dictate. Once you start mixing and pumping, if you're not seeing the curve leveling off, then you can begin hesitations, and that's independent of the type of formation.
Next question, is it recommended to perform an inflow test after squeezing cement into a perforated formation?
I'm not sure what is meant by an inflow test. If it's a negative test, and I'll just speak to this generally. If I don't answer your question, please reach out to me on LinkedIn. But you want to check both for negative and positive flow. And if you remember, I was talking about on the squeeze where you check for flow back after you obtain the initial squeeze pressure. So you're checking for flow back into the displacement tanks on the cementing unit. You don't want fluid to be coming in to the perforation tunnel and continuing to flow up into the pipe. So you want to create a seal from a negative standpoint, but you also want to create a seal from a positive standpoint. So yeah, just checking it both from a negative, the squeeze both from a negative and positive standpoint. You do want to do that after you achieve the squeeze pressure, and you can do that at the time while the pipe's in the hole.
All right. Next question is, could you comment on the term microannulus? And for example, if there is one, is it detrimental to production, or is it more or less a benign artifact?
Microannulus is more problematic from an identification standpoint using a cement bond log. A microannulus will complicate a CBL from that standpoint. And the way to remedy that is folks who run CBLs, if there's any doubt or if there's any concern about a microannulus, they will simply apply pressure to the casing and expand it out. From a production standpoint, not much of a concern. The microannulus is too small for wellbore fluids to flow back up. And if you do have migration of fluids, it's probably something other than a microannulus, like a channel at some point. So it's more of an issue from being able to just interpret the cement bonding to the pipe.
Okay. Next question is, for suicide squeeze, is it not better to place the CR near the top perforation to reduce the risk of getting stuck in cement, especially if circulation interval is quite lengthy?
Yeah. Well, then it wouldn't be a suicide squeeze when we set the retainer above the top perforations, but it'd be the entire objective of the, and I'm going to call it circulation squeeze. The entire objective of the circulation squeeze is to circulate cement into the annular area through the bottom purse back up into the top purse, and that's the whole gist of that system, and hence the word suicide from the standpoint of setting the retainer above the bottom purse. But no, it has to be set above the bottom perforations to do the circulation that we want to achieve.
Okay, then the next question, for a squeeze job, do we need to use the balance plug method, or can we only dump cement into the perforation area?
Well, a balance plug method is when we set open hole plugs, those are typically designated for open hole environments. Now, I did use the term when we were talking about the Bradenhead method on setting a cement across the entire perforations, and that was like balancing plug, sitting it internally in the casing. That would, well, with the if the question is being asked, do you need to spot the cement across the entire perforated interval from below, then come up above, or can you simply be above and inject it into the Bradenhead, the top perforations? You can do that. You can do that. The advantage of setting the tubing down below through the perforations is you assure that when you start, that you'll have cement across the entire perforated interval. If you want to start off with the Bradenhead method and have the tubing set above the top perf and inject from there, if you're more comfortable doing that, then that is certainly an option with the Bradenhead method.
All right. Next question, we've just got a few more here. If fracture pressure is unavoidable, then what are the chances of a successful squeeze job? Well,
they're not totally zero. It's just that you fractured the rock and you're going to place cement into it, maybe a little bit more cement than you were intending, but it's not a total lost cause if you're squeezing perforated intervals. There may be a likelihood that you can squeeze all the perforations, but it's just much better if you can do it with a low fluid loss system. So I would say if you're in an environment where you exceeded the fracture gradient and your intent was not to do it, then there still may be a chance that you'll obtain a successful squeeze.
All right, and then we got a couple different versions of this question, so I'll paraphrase. In areas with little to no offset data to go off of, are there any rules of thumb on percent excess in cement volumes?
The only rules of thumbs would be the ones I shared with regard to injection rate and number of sacks. 2 barrels per minute, 100 sacks. 50 less than that